Well, welcome everybody to another brief educational video on the outcrops. I'm here with Brandon.
Hello.
And obviously our expert video man, Chris, from Geology Field School. We are in the Ainsa Basin in the Spanish Pyrenees. One of my favorite places to come and look at deepwater outcrops. Here and probably San Diego, California are the two places where you can see all the different facies in a blast of time. So it's a really cool place to go. So what we'll do here is we'll walk through one outcrop of one part of the succession here, make some observations, make some interpretations, and then we'll talk a little bit about seismic response and geophysics for those of us that are working with seismic data. So just to set the scene, we're in the Ainsa Basin in the Spanish Pyrenees in the Eocene. So at that time this was a deepwater succession, and we are particularly standing at a place where we see some coarse grains, gravity flow deposits of what is called the Morillo Formation. It just happens to be the formation name, but just in case you know this area a bit, you probably will be able to recognize the outcrop. So we'll have Brandon make some observations of the different rock types first as we walk a section, and then we'll talk a little bit about it.
All right, starting here, we're looking at the base of this outcrop, and we have about 1.5 meters of kind of background mud, which has a bit of a calcareous component to it. We can see very thin stringers of dirty material in there, but in general it's all very uniform, fine grained mud with calcareous component to it. And then as we go further up, we get this erosive based sandstone that is very poorly sorted, kind of fine to coarse grain sizes, some larger classes within it. There's a number of different units within here, very erosive bases within all of these. If we look up close here, we can see that just an idea of just how variable the grain size can be. We have some very coarse sand grains, we have some large benthic foraminifera here. So there's a lot of different grain types here, very poorly sorted. And that's kind of true through the bottom part of this unit. As we go up, it starts to get a little bit more organized. We start to see some kind of lineations through here. They're set by these little holes, these little pockets. These are where larger benthic foraminifera have been eroded away. So they will form little layers there. And we go follow that up. We get to the top of this thick sand, and then the world changes a little bit, right? So we come over here, we see another big block of sand, and you know, it looks a lot similar to what we have below, but then up there just above it, kind of where that tree is, we see there's a lot of big, large clasts that look like they're made out of the same material that's below. And some rounded clasts in here, some rounded cobbles. Here's some kind of big tabular cobbles, more rounded cobbles. Fine mud matrix here. With little small granules within it. So there's a lot of variability. Things have changed quite a bit. We had some organization, now it's very disorganized. This goes on for quite some time. If we stand back a little bit, you can start seeing some lineations within here, some overturning, some contortion within this. And then it goes all the way up to a sand cliff face above, about 5 meters thick worth of material. This is what we think is kind of a debris flow slump deposit that formed on top of those sands deeper down in the basin. Towards the top of the debris flow in the base of the sand, if we look underneath, we can see a lot of these features. They're very bulbous shaped, dropping down, and they kind of thin out in this direction. So these are flute casts at the base of the sand. And if we look in the sand itself, it's still poorly sorted, but the grain size variability is smaller. Here again, we see a lot of these really nice linear features here, but these are set up by the dissolution of those those larger benthic foraminifera throughout. So a little bit more organized, a lot less internal erosion and contortion, more uniform grain types in there. Again, mostly just the sand, with the exception of the layers of the larger benthic foraminifera. And that comes up to the top surface here of the sand. again, we've looked at about a meter and a half thick of sand. And then we get back into some kind of finer grained recessive material here. Here we can see a lot of contortion and mixing and overturning within this as well. We don't see a lot of really big grains in this at this point, but if we look up there, we can see some larger cobbles, but then a really big boulder as well. And coming down here, we can see nice folding within this fine grained material. So again, we're back into another slump debris flow type of situation. So we had a sand in the middle of the debris flow, another debris flow, and then if we go to the top above, we get to another sand where again we see some flute casts in the base. At this point, we're starting to get really well organized. So we do have some very coarse grained sand here. The sorting's not quite as bad as we saw in the past. We don't really have as many granules in it. It starts to fine up a bit till we get into some medium sands up here, planar laminations, and then it gets fine grained sand at the very top. And if we were able to look at the top, you could see that it is ripple laminated. And then finally, there's a very fine bed of sand on top of that is ripple laminated as well, followed by a thin layer of this really dark gray mud, and it's very soft mud. And then some other sand beds, and then again up into another sand body. This one, maybe some weaker flute casts. It's harder to tell on this one, but we have this thick block of sand. Again, this is more organized. It's coarse grained sand. You can see some parallel laminations within it. That followed by some mud, then some kind of erosional based sand here. The sorting is kind of more poorly sorted at this point. We have some larger grains in here, some granules even, and that continues into this very thick sand unit. And if we were to go all the way to the top of it, we see that it starts to get organized a bit again. The grain size decreases. We get into coarse to medium grain size sand here. And finally, as we move forward further left, we start getting into thinner layers of fine to very fine sand and muds up until we get to the top of the unit over here. And so if we look at this again, so we have these thin sand beds. They're very fine grained. They often have ripples on top of them on the surfaces. And here we have a thin sand with some convolute bedding. And here's some more contorted, fine grained mudstones, and then some more contorted sands. And then we're kind of at the top of our outcrop.
All right. Oh, thanks, Brandon. Very good description. So, it's good to, as Brandon kind of showed, to go through the basic observations of description without making too many interpretations, and then kind of think about everything we walk through. So, kind of summarizing a few key points. One key point in this outcrop is what I would call Lithofacies diversity. There are a lot of different rock types that we see in here. So we have a significant grain size spectrum. So we've seen things that are the size of boulders all the way to mud and everything in between. So there's a lot of different grain sizes, and we've seen them organized in a lot of different ways. So we've seen things that the mud and sand and these large blocks are all together in very disorganized looking areas. Then we see some areas where the sands are coarse grained to fine grained, so there's not much mud in there, but they're still very poorly sorted. We see some medium grained sands, some fine grained sands with current ripples, with parallel lamination. We see some slumps. So before you quickly add up 5, 6, 7, probably about 8 different facies you would call in here. So there's a lot of diversity of the facies. That's one thing. The other thing is, as we walk through it quickly, it's kind of hard to get an idea of organization in there, but as Brandon and I have measured this section in detail, we can kind of summarize that a little bit in here. So there is a stacking pattern to this that is actually really quite predictable and recurring in a lot of these places. So this whole section is about, what we walk through, about 30 meters in thickness. And right at the base, those sands at the base, very poorly sorted. So about a couple of meters thick. Now we're kind of gonna go interpret there. We don't really see very good indications of flutes, maybe a little bit on there. So these are probably not turbulent flow deposits. These are probably hybrid or even mass flow deposits. So it's a a kind of a sandy debris flow deposit at the base. And then we go through about 12 meters of a mud supported rock type with actually the coarsest material, the coarsest grains in the size of these boulders, but the matrix is muddy with lots of sand grains in there. So again, that really disorganized motif is a deposit of a debris flow, so a muddy debris flow. And then we get the sand bed with the really nice flutes on there. So there's several sands in there, coarse to medium grained, still fairly poorly sorted, but you know, getting better reservoir quality. Then we get our 2 meters of slump on top of that, and then we start getting into some more organized sand bodies with more porous sorted sands at the base. And then, as we've seen, there's some parallel laminated sands in there and some current rippled sands. You know, one of the interesting things, if you interpret this back in the old days, every sand that we could possibly conceive in a deep water must have been deposited by a waning turbulent flow and deposited what we'd call a Bauma sequence. So there was an A, B, C, D, and E of a Bauma sequence, where the A would be normally graded suspension settling sand, the B would be parallel laminated sand, the C current rippled sand, D siltstones, and then E would be the mud. And often we see that in the upper part we see that parallel laminated sands and current ripples, so those look like Bauma sequence, but these thick basal parts of the sands, we call them A, Bauma A, but they were really not well sorted and normally graded. They were quite poorly sorted, so often we can see actual evidence of traction, larger scale bed forms in there. So they're actually being deposited by traction, leaving a slightly poorer sorted sand rather than a really nicely normally graded sand. So you can see that motif of more debris flow dominated, muddier stuff at the base, some nice thick, better sorted sands, but still a lot of traction, and then towards the top you get these fin bedded sands and muds. And that's a very typical succession, that stacking pattern, that facies diversity of what you would see in a confined fill or a channel fill. Now we've got drone footage here that will kind of showcase that a little bit better. It's hard to say from the outcrop whether it's confined or not, but this is a very typical confined fill, and that 30 meters is not an unusual thickness of a single fill, of a channel fill. So why do we care? That's kind of what we do here, other than just help you recognize the rock types. One other thing in these channel fills is net to gross. So this is an entire channel fill, and while we have some very coarse material at the bottom, a lot of that is very poorly organized in these debris flows and these slumps with a lot of mud, so there's actually very little reservoir, and a lot of the reservoir is actually distributed in this sort of middle to top part before it gets really flaggy and thin. So if you did a little net to gross on this, I'm going to give you a little piece. So if you were doing net to gross on a channel fill, you know, the question is at the bottom, would that be reservoir quality or not? In my experience, typically tough. Might depend on the fluid type. If you're looking for oil, it might be a tough one. Maybe for gas, that's okay, but maybe a couple of meters there. And then you start adding these meters, so you've got somewhere between about 14 to 60 meters of net reservoir in that 30 meter thick fill. So about a net to gross of 50%. That's really not that untypical in an actual part of a channel fill. So it may not be as high net to gross as you think, because you got all this really coarse, poorly organized stuff to deal with. So think about that. The other thing that's really cool here is to think about the seismic response. So given that facies diversity, you get some really unique and quite maybe non-intuitive to some people seismic responses, in that these basal deposits, because they're poorly sorted, are really hard. They're very low porosity. So they're high impedance relative to these better sorted sands at the top that are typically lower impedance. So assuming a sort of background, more calcareous mudstone, and just for playing this game along, let's say that the sands are a little bit lower impedance than that background, and these are higher impedance. I've drawn a little impedance curve here. So the impedance curve here goes from high impedance to the left to low impedance to the right. So you can see the way I've drawn it. I've drawn some really high impedance rocks at the bottom here, which are these debris flows and some of these poorer sorted traction beds in the sands. And then as the sands get better sorted towards the top, you actually get into a lower impedance, and then back to the background mud. So what seismic response does that generate? So if I draw, you know, I don't need rock dock, so I'll just draw a little seismic wavelet here on the paper, and if I say I'm just going to look at this as sort of a tuned response of seismic, I might see something on a near stack of data or a full stack of data that has a really high basal high impedance unit, and in my color convention I've kind of colored that as a red peak, so that will be a tuned high impedance response. And then towards the top you might actually get a very weak, almost non-existent low impedance response. In this case I color that kind of a blue. So you may see the base of this channel fill really clearly as a very strong, bright, high impedance bright on your seismic data, and maybe not quite appreciate the upper part of it. The far off stack of response of that tuned response would be a kind of a class 1 dimming. So my strong high impedance peak, colored red here, is going to dim on the far, and then this weak low impedance response, which would be a class 3 response, is actually going to become significantly lower impedance and become much brighter low impedance. So on the near stack you might really kind of get the hint of the base of these systems, and on the far stack you'll get the top. The key with this is, when you see that sort of seismic response, it's very typical of a channel fill. Right, this high impedance base with the low impedance top. The net to gross is not necessarily in the brightest stuff on your nearer full stack at the base, quite the opposite. It's more stacked towards the top. So think about that when you're mapping these guys, and really use your full range of angle stacks to kind of decipher things, because these channel fills are really diverse in facies and therefore also very diverse in their impedance response. And obviously I've kind of drawn something fairly simplistic here for reference, but depending on thickness, frequency of your seismic data, tuning, you can get a whole range of fairly non-intuitive responses that, if you haven't really seen these rocks in outcrop and understand what the most likely response of these channel fills really is, it's going to be really hard for you to decipher these and hunt for them, and secondly appreciate what the most likely net to gross distribution is in there.